All right. Thank you everyone for coming. To those I haven't met, I am the new chair for the VGS for the 25-26 season. Just to give you a quick update on events you've got coming up. On November 26th, we have the legacy lecture for Dr. Finn by Jason Rowling and Thavaraj. So stay tuned for that update. We are working on a talk for the 13th. It's still not confirmed. It may not happen, but just keep an eye out. So we'll let everyone know. And without further ado, I'd like to bring up Saman to introduce the speaker. Thank you.
Thank you. Hi everyone. For those of you that don't know me, I'm Saman Zarnani, geotechnical engineer with BGC Engineering in Vancouver. I have the pleasure of introducing Mike tonight. He asked me to keep it brief, so I'll do my best. And I think all of us agree that Mike doesn't really need an introduction. His name is synonymous with critical states, soil mechanics, North sand, and static liquefaction. His list of accomplishments are long. They are on the flyer if you're interested to know. But one thing I wanted to share with you guys, something I personally admire about him, working with him over the last few years on a couple of projects, is his ability to bring in different strands of our long history of our geotechnical engineering knowledge and putting them together to create a coherent, usable framework for us as geotechnical practitioners that then we can put into use. His strong technical, analytical capabilities are complemented with common sense, practical engineering solutions, and I think that's a combo that all of us should adhere to or try to achieve. So with that, I will pass it on to Mike to lead us through his presentation. Please join me in welcoming him.
Thank you. Right, good evening everybody. And pleasure to see some bunch of faces I already know in the audience. This talk is based on a paper that Ian Gordon and I have recently written, which is now in press. It comes out of the Cadia Dam slump, and that is the picture you see in front of you, the dam with liquefied tailings flooding out onto the toe. I was part of when you have one of these failures, there's always a search for the guilty, which is just done through establishing an international review board or words to some effect. Well, that's a collection of 3 or 4 individuals, and they have limited ability to drill boreholes and push CPTs and do lab testing. So ITRBs are supported by a consulting organization. In the case of Cadia, that consulting organization was Hatch. Ian was the lead for Hatch, so in formal terms we'd probably call him the principal investigator for Cadia. So I really depend, without Ian, the board would have had nothing. It really is, this is a goodly part of his story. If we look at what happened on the slump, this is kind of an air photo of the thing. The grid lines are a 1 kilometer spacing, and the northern TSF, the slump was where I have in the white marker. Basically, it failed on the corner there, and the failure was entirely contained with the southern TSF. So there was nothing released to the environment. When I look at the fluster and flurry and excitement in Australia, I'm going, hang on guys, you've had no breach of the impoundment boundary. You've had, this is an internal issue. But everybody got terribly excited. And of course, we're happy if they get terribly excited because they then give us money. We can get to do things, which we duly did. The soil that caused the problem or the cause of the slump has a undrained strain behavior like this. And when you look at that, that's pretty much a classic liquefaction stress strain curve. You come up to the peak, we go zooming down from the peak, and it's all a bit brittle and it all happens rather quickly. However, that is not the tailings. That is actually the foundation. It's a unit called the Forest Reef Volcanics A, or FRV-A, and that in the slide in front of you, that's the stuff in purple. Okay? And I'll come to a little bit more detail on that unit in a second. What was going on at Cadia, and I'll get my trusty pointer here. What we had originally in green was a conventional downstream constructed dam. And then as things go on, people say, well, let's go upstream and save some money, etc., etc. So they switched to upstream construction, which is what you see there going up in green. And then somebody said, whoops, this stuff looks liquefiable. We'd better put a stabilizing, and they were worried about this and blowing out like that, better put a stabilizing buttress in, which is that thing there. The intention was to put a further stabilizing buttress on this whole slope here. Well, they hadn't done that yet because there was a pile of rubbish at the toe. So they excavated at the toe to clear out the rubbish. Now you already know where this is going. The road to hell is paved with good intentions. So we're steepening the slope and digging a hole at the bottom. This is not a good plan. But anyway, that's where they went. This is a stratigraphic profile through the foundation rock. And I probably should back up a slide and tell you one thing. When this dam was designed and construction started, the thing extends over whatever, a couple of kilometres or a kilometre and a half. You know, it's quite an extensive thing. But the foundation in that area was mostly competent bedrock across the entire footprint of the dam. So the engineers of the day said, okay, we'll expose the bedrock and get rid of crap on top of the bedrock, and provided we're on competent bedrock, we don't really need to do a great deal of site investigation because we know geologically we've got a regional piece of rock. That is true in general. However, down the corner where the dam failed, what we had was basalt that had flowed over the previous volcanic stuff, and that we'd had the earlier stuff had decayed, become residual soil. So we had actually quite a weak residual soil, but it was masked by what appeared to be competent rock over it. So this stuff was never picked up at the site or when the dam was being constructed. And to be honest, I have also engineered dams based on bedrock and said, let's do it. I think I would also have been caught out on this one. But anyway, that's what the story of this failure is. It's this stuff in here. We don't need to worry too much about that stuff there. And that really was along for the ride. The story is about the forest reef volcanics. This is a view of the failure looking from the top. And these are the investigation boreholes, because this forest reef volcanics is actually, or appears to be, quite a narrow corridor. So finding samples of it was actually quite a challenge, to finding where it still existed. Now, you know, the obvious thing to do would be to go in there and drop a borehole down there and intersect the forest reef volcanics upstream of the failure. That idea was indeed proposed. It was killed on health and safety grounds that we weren't allowed access. Ian came up with the remark, we had a bunch of geotechnical engineers from both the board, Hatch, and a couple of other consultants, and Ian pipes up, we have 800 years of geotechnical experience in this room. We all want to go there and you won't let us. Anyway, we were constrained with where we could go. So that's where the boreholes were done. This is what the material looks like. In terms of a grading curve, you see up there, it's kind of a mostly silt, a little bit of sand in it, and a chunk of clays. That's what it looks like when you get a sample and chop in half. The white veining is kaolinite. What I found very surprising is if you look at the right-hand plot, those are some void ratios of the as-recovered samples, plotted versus depth, I believe, yeah. The solid symbols are the void ratios of the samples we tested. Laura sod, some of the samples we didn't test actually had higher void ratios. But we're talking void ratios in the territory of 1.4, 1.2. This stuff is loose. Now, bear in mind, originally, this was a volcanic rock that's been had a whatever a porosity maybe of like 1% or 2% or 3%, and we've lost a lot of material through chemical weathering. And we've got a very loose structure. So surprise, surprise, it looks like a liquefaction failure. Okay, this is odometer test, or 3 odometer tests at the top, which are this coloured lines there, there, there. So we managed to get odometers on material. The other things are traxial tests, where this is the void ratio of the traxial test as recovered, down a borehole or in a couple of American trial pits. And then we consolidated them to the stress range we thought of interest for stability of the dam, which is that grey zone. And that's a consolidation trajectory. Most of them more or less follow the odometer curve, so we felt they were preserving original structure. There's one there, you can see PEng, that one, we had a lot of disturbance in the sample, which then collapsed as we brought it to interesting test pressure. Now, a feature of residual soils, and this is a residual soil, is they don't have any pre-consolidation pressure per se. They've just chemically weathered in situ, there's no prior loading. And the interesting question is, okay, if we take one of those odometer tests or another one of those odometer tests, what is the real fundamental things going on? It looks like a very interesting curve which comes to a sort of pressure and drops down like a stone. What is the physical process underlying that curve? Well, the way you can start digging into that is, rather than plotting E versus stress, you differentiate the odometer curve and plot the confined modulus. So you turn it into a modulus. So that's what we've done here. Those are the same odometer tests you've just seen in E log P space. We're now turning those curves into a confined modulus incrementally, and we're plotting against effective stress. We're no longer on a logarithmic scale. And there are really, see if I got it. Yeah, there's the initial phase, or up to a pressure maybe of, say, 600-700 kPa. The modulus increases with confining stress. That is a standard C sub C idealization, or slight power law variation of it. That is absolutely normal soil behavior. Effective stress, double effective stress, you double the stiffness as well as doubling the strength. However, when you get up to, for these soils, when you get up to, see if it comes up on the screen, yep, up to a particular pressure, then all of a sudden the modulus stops increasing. It just runs constant. And then you come to another pressure, such as there, and not only is the modulus now not increasing, it's actually decreasing. So we're into a crushing soil. And the whole thing is going downhill and becoming worse. Interestingly, in 2 of the tests, it actually seems to bottom out at a constant modulus of a very low value. I presume at that point we've squished it all together. But that's the kind of behavior we're dealing with. Now, I have to give you a bit of theory, because otherwise the next explanation won't make sense. The undrained condition is not Poisson's ratio equals 0.5. Under a elastoplastic model, we break strain into elastic, plastic components, and the undrained condition is simply that the 2 added together equals 0. The elastic one is simply the change in P divided by the bulk modulus. So we get an expression for change in P in terms of the bulk modulus and the latency times the shear strength. Well, the latency comes from the stress to latency law. So what we are able to do is link dP to eta. And what the key to this is, if dP is greater than 0, then the stress path will bend to the left when plotted in a normal sense of a QP plot. So we have to have eta greater than m for the stress path to bend to the left, which is that thing. Now, back to my first slide. We can see what m is down here. We're getting the end of test conditions. So my green line is just a straight line through the end of test conditions. You'll observe at point B, the stress path is bending to the left. And it's bending to the left above the green line. What that tells you is up over here, eta is greater than z in M, i.e. there is a different value of M there than down here. So we're dealing with a structure which is manifesting itself as an M that evolves. This is one test. We have a bunch of tests, and they all show similar behaviour. If you want to put it in more Coulomb terms, the residual after a decent amount of strain was about 16 degrees. But the peaks are quite high. The strength trend, the high stress tests, which are basically tests that have gone past the crushing point, they have particularly weak values, or weak values, they're like normally consolidated values. You have a claggy clay and you know nothing much else about it. SU over P naught is about 0.25, 0.27, give or take. That's spot on what we've got with this stuff after crushing. But before we destroy the structure, we have quite a dependence on void ratio. And on the ones that aren't too weathered, are really pretty decent. You know, an SU of P 0.8 is not to be sneezed at. And there is quite a strong effect of the erosion effect on void ratio. Once we get down to these void ratios of 1.1 or 1.2, we're back with a normally consolidated material. So, in our profession, we actually have two soil strength idealizations. We have our friend Terzaghi, which uses the Moore Coulomb criterion, and that is not used in critical state models. We have the Taylor-Bishop idea, which I'm going to show you in a moment, which says that soil strength has two components, what's called friction and interlocking. And this is the Taylor-Bishop model. The photograph top right is Don Taylor, bottom right is Alan Bishop. Don was an associate professor at MIT in the late 30s up to mid-40s. And what Don did, he did a lot of shear box testing for Fort Peck dam failure amongst others. And what Don noticed is when he was testing sands in a shear box, if he was testing a dense sand, the weight on the hanger would rise up as the sample dilated. Well, Don did a calculation and he said, hang on a second, out of the work done, that is the force pushing sideways times the distance travelled, that's the amount of work done, 30% of that work is expended in raising that weight. So he said, okay, there's something going on here, and Terzaghi's got it wrong. And we need to account for the movement of work against confining stress. Don put his findings in his book, which he published in 1948. Curiously, he never put an equation to it. You can read Don Taylor's book, and it's a wonderful textbook on soil mechanics, despite it being now, 60-odd years old. But he always dances around mathematics. Alan Bishop was the guy who said, actually, we can put an equation to this, and that sketch there is taken from a piece of work by Alan Bishop. Now, in those earlier days of soil mechanics, today if you think you've got a great discovery, you write a paper. Back in the 1950s, if you have a great discovery, people would rush off a letter to the editor of Geotechnique. So you have a 4-page submission, and with the absolute gem, but it's not indexed really by a title or anything, right? And that's where this figure of Alan Bishop's is hidden. It's in a correspondence. And Alan derived this equation here. And what interlocking, today we just call it maximum of the latency, which is simply the slope of the volumetric curve versus axial. That's the critical state there. And they call friction what we today would call the critical state friction. So the coloured annotation is my own. The diagram behind it is Alan's. In modern parlance, this is conditioned on a shear box. We would look towards generalising to stress invariance. We'd write that as this thing here, eta, which is Q over P, or in 3D, it's sigma Q over sigma M, equals M minus dP. And that equation is embedded in pretty well every modern constitutive model. You may find there's a little coefficient put in front of the M minus dP. For example, the sandy sand, there's a little modifier in there. But in principle, that's our equation. And that just goes to that. Now, that equation was derived or started from testing on reconstituted loose sands and dense sands, but reconstituted samples with no fabric. It was subsequently, there was an investigation into clays using at Imperial College, and God help us, they took like 6 years to drain triaxial tests on clays, which involved like 4 theses, and they started out by taking some London clay, digging it out, and they put it in a blender, mixed it with the distilled water. And they made a stockpile in like an oil drum of this reconstituted, wetted up, structureless London clay. And that then became the inspiration behind original CAM clay. So where do we put structure? So we have this constitutive model or basic stress to latency law derived from an understanding based on structureless materials. What do we do with structure? Well, various people have proposed different schemes, but they all come down to much like this. This is taken from a paper in 2000. These are horrible things, but I'm going to try and lead you through it. These things here are called there, and you draw a line through it, and you've got this sort of banana-shaped surface. That's called a state boundary surface, and that's supposed to be the limit of any soil's accessible void stress space. The one over here, which I put reconstituted, is the kind of thing you get testing structureless sands, soft claggy clay, etc. And what people said is actually what we can do for natural soils which have structure is we just push the state boundary surface or the yield surfaces outwards. So we've gone from here, which is structureless, pushed it out there, and so that's how we put structure in. So we just expanded the yield surface. No problem at all. And this is quite embedded in our literature. Now there's a problem. If you have an undrained test like we have here, and there are 2 components for pore pressure. There's a component that comes in here from changes in total stress. And if you draw a vertical line, the bit from here to here is caused by plastic strain, the equation I showed you earlier. So here we have, from the get-go, a structured soil. I'm generating excess pore pressure from the start. If I go back to this expanded yield surface, if I've expanded the yield surface out here, and I'm down in here, there should be no excess pore pressure, because it's elastic. So what we've done, it's just gone too far. Now, in defense of these people putting this stuff, they have not pushed it forward for residual soils. They've done it for structured soils, whatever they are. But clearly, residual soils are within the topic or category of structured soils. So the question then is, okay, what are we going to do? Now, the Terzaghi, what's called the Terzaghi strength model, uses the idea of Coulomb, which is the chap in the oil painting, top right, from 1776, and he just flipped it into effective stress terms. And the objection to this model is, if you look at typical soils, you can't see a bond between particles. Hence, people said that cohesion is inadmissible. And that was the basic objection of Taylor and Bishop to Terzaghi's teaching. You know, where they looked at the particle contacts, they simply weren't there. That is not true of residual soil. We have a decaying thing, and the structure of the residual rock, or the original parent rock, is still there. So, what should we do? Well, Terzaghi has cohesion but no concept of dilatancy. Taylor Bishop has dilatancy intrinsic to soil strength, but also has no bonds between soil particles. But they're not mutually exclusive. Why don't we just cut in cohesion on top of Taylor Bishop and say it's possible to have cohesion with dilatancy? So what we proposed was this. We said M, our critical state friction ratio, composed MR, which is our residual value at large deformation when we've broken all structure, and MS, which is our structural component. And at the back of the minds, when this was put forward, we thought MS would be 2C, 2 because we're going to flip from cohesion, which is in SU space, to Q space over P dash. And we said, okay, what we'll do, we'll run with M, which has got its structure in it, up to a certain point. And then we will allow M to decay such that over here I'm on MR. So I'm introducing, if you will, a cohesion into critical state. And I'm introducing, I haven't put a cohesion in, I've got to have a decay law. The question comes, okay, when does decay kick in? We used two criteria. We said, okay, after peak undrained strength, if you see the stress strain curve dropping, well, patently, you're starting breaking things. So that's one trigger criterion. The second trigger criterion was if P dash C exceeded the crushing pressure, which we say identify from the odometer tests. So we had this variable floating around, we have this crushing pressure. So you may say, okay, I've got three parameters now. I've got MS, I've got the rate of decay of MS, and then I've got my crushing pressure for when MS kicks in. This is the data at the onset of structural breakdown. So this is when either I'm hitting my crushing pressure or I'm hitting peak undrained strength. I've also put the odometers on this figure. The odometers are the green diamonds because in an odometer test, you do have Q as well. It's not just a sigma V thing on it. So if we assume that K naught is say 0.6, I can convert this, the sigma V into a shear stress as well, and that allowed me to how I put the crushing pressure of what we observed in the odometer test into this plot. The blue dots are all triaxial tests. We can inspect the triaxial test and say, okay, there is a peak or when we get ourselves into crushing. Now, when I started down this road, on the story behind the idea of residual soils, and I've got some built-in structure from the parent rock, I was expecting a true cohesion, which is that blue line. And frankly, it's not there. The data has a very clear gradient, which you see there. With hindsight, and my co-author berates me for my stupidity, we probably should have gone with the blue line I show on the screen. But what is in the paper that accompanies this talk is the black line. I was just wedded to the idea there has to be a bit of cohesion. Please, Lord, give me a bit of cohesion. So that's what we went with. So, to North Sand. Those of you who are not familiar with North Sand, it's got a handful of properties, literally about that. Normally, when we're determining critical state loci, we do a whole bunch of samples, each of which is same material, whether it's in clays or sand or whatever. So I can join points together to estimate where the CSL is. I can't do this, where each sample is different from its neighbour. Right? So what did I do? So what I did, I said, okay, for the purposes of this, we're only looking at quite a limited range of change in P dash in a triaxial test. It's actually good enough to assume a semi-log for that, even though we've actually quite some extreme curvatures because I'm only operating in limited range. And we assume, because we're dealing with very loose soils, that lambda 10 of my CSL was the same as C sub C. Now we allowed C sub C to be different for each of the triaxial tests depending on the initial confining stress. But that's how I'm picking up my compressibility. And the kludge of lambda 10 equals C sub C, that's not bad if we're dealing with loose materials. Okay? Remember, my void ratios was 1.1, 1.2. Not bad. My next property is the volumetric work coefficient, N. And there's absolutely no way I could recover that from the available test data. I've looked at many soils over the years, and N always seems to come out about 0.33 or a third. This is suspiciously close to our friend Don Taylor, who said a third of the work has been going there. But anyway, my go-to number for N is about 0.3. For some reason, which escapes me, we actually put 0.33 in. I really should not have had too significant figure accuracy. That's a myth. It should have been 0.3. Oh, sorry, we used 0.35. I should look at this standing in front of you. I'm sort of shaking my head and wondering, what on earth did you do that for, Mike? Now, state latency is a key parameter. That tells you how changing void ratio changes the limiting dilation rate. Again, we can't do replicate tests. We've got to make an estimate. Over the years of testing various soils, a pattern emerges as to what value this thing here looks like an X. It's actually a Greek letter C or chi. That parameter represents the ease with which particles can move past each other. So a high value of chi means it's actually quite difficult for the particles to move past each other, so things have to happen quite rapidly. Conversely, we have a lot of void space, and the things can take a very relaxed attitude and have a gentle stroll as they dilate. So we get a low value of chi. From my testing experience, the test data that's been put in front of me, clays and soft soils tend to a chi of around 2 to 2.5. So like soft claggy slime tailings, 2.5 is not an unusual number. Well-graded soils, and here I'm very influenced by Bennett Dam, tend to be much greater than 6. At Bennett Dam, the core of Bennett Dam, we were looking at chi values like 8, but Bennett Dam is a cooked material where they've tried to put silt particles within the space between sand particles, and we have this uniform where it's almost fractal. We've tried to fill every piece of void space with a particle. So there's very little free void space for movement, so you get this very intense response. Here, I'm dealing with a well-graded material, but equally with very high void ratios, and what looks like very compressible particles. So I said, okay, I want something between 6 and 2, so I use 4. And as it happens, 4 is not a bad number anyway for a lot of materials. Having said that, this is not it turns out when you're going to show you the tests, a lot of the tests are actually around the critical state. So this is not a particularly important parameter. And then the other two, which is the stiffness and the elastic modulus, I just iterated those to get the best match to the stress strain or the stress path. So that's how we fitted it. And playing those games, this is an example of the fit. We got to one of the triaxial tests. Very nice. Blue is what we fitted. Brown is what we measured. Another one. Another one. And this one's really intriguing, because if you look at the stress path over here, you would have said that was a messed up test. But when we put this crushing model in it, it just nails it. At this point, I've introduced 3 simple ideas, and this sort of stuff starts emerging. You say, hang on, Mike, you deserve a beer for this. This is pretty good. These are all contractive tests. The dilative ones are not quite so good. This is one of the better fits to the dilative samples. It comes up, but we're just not quite as good as the contractive ones. This is getting less good, and this one is pretty poor. But let me go back here and show what the problem is. You'll notice here on the stress path, we've put in we've got our M plus structure over here, and that's why we dilate up to the structure plus residual line. And the model can't do anything until it gets there. The real soil seems to know the residual value, even though it then continues to dilate strongly, as though it also knows about that one. So when we have these dilatant soils, they seem to know both values of M at the same time. Now, I played various games with trying to say, let's pretend it's non-associated. Let's have both M plus S. So M equals MS plus MR, and M is just going to be MR in play at the same time. It just blew up the theory. I could find no way of reconciling such a difference. So this is as good as we can do with the dilatant materials at the moment. And if any of you got an idea, and we'll come to the discussion of what might be going on, I'd love to hear it. Okay, so we look at the large deformation strengths. I'm just picking the MRs just directly off the tests. There's no obvious trend with as sheared void ratio. If I plot it against initial confining stress, one is tempted to say actually there's an effect as the confining stress goes up, the residual value comes down. Maybe that's crushing of the particles. But, you know, it's one of these things, it would be nice to have another 20 data points. But that's one of the constraints of these review boards. You're basically hired and you're given 6 months and it isn't a research project. So you get some boreholes done, you've got to run with what you have. Yeah, it would be nice to have had a bit more tests. Now the decay, this is the structure which we're going to put on top of that, and perhaps there's a weak dependence of structure on void ratio, which is the dotted line. I'm slightly loath to call that as real. This may just be random because like these residual soils are not remotely close to uniform. You know, they jump all over the place. So what we may be looking at is just simply the random variation in the FRV-A. The decay rate, though, showed a much happier pattern. The curve I showed you, that simple exponential decay, you characterized by just a parameter alpha, and that did seem to be, the looser you got, the faster things happened in terms of breaking down. And that seems to me, you know, physically plausible. What is interesting, when I'm modeling these tests here, back up, I'll go to the things, the end point of the stress paths, there, whatever, and also in the case of the dilating ones, the end point is controlled by state parameter divided by lambda. So I can actually, and I'm fitting the end point. So given I've assumed a lambda value based on the odometers, I can actually calculate the state parameter because I've actually fitted the endpoint. And the reason I fitted the endpoint by varying the lambda, the state parameter. And that is the state parameters I come up with. There seems to be some sort of trend. The stuff is around its critical state as the current stage of weathering. Don't take it from me that suggestion that if weathering continued, it can't get looser. Okay. I'm half tempted. I put this trend line through it, but you could also plausibly say perhaps you have one state parameter to arrange your crushing regime, and then it rapidly decays to a much looser state. That would be also a model or an idealization. Sad thing is, you know, I'd kill for another 10 tests. I don't have them. This stuff was difficult to find anyway. Triaxial versus direct simple shear. Those of you who have read the Cadia report will know the board put a lot of weight on direct simple shear. There's some examples of direct simple shear, and there's a triaxial test at roughly the same confining stress. The post-peak, the endpoints are not a million miles different. But the direct simple shear simply does not show up the structure we saw with the triaxial test. Now, truth. Well, if you're on you well know if you've got a case history and you're doing limit equilibrium, you just assume the factor of safety is 1 and then calculate whatever your strength you're looking for. You can't do that with a brittle model like we're running here. We know we've got a material whose properties are changing. We don't have a simple rigid, perfectly plastic stress strain curve. We've got something that's yielding, something that's decaying with strain, and it is loading up somewhat plastically. What was done was to use flak, and the various properties were changed to try and replicate the observed pattern of deformation. Okay, that's why I call it iterating to failure. We're trying to guess properties and see how things are coming in. What's quite interesting, we had tailings liquefied over there, and the best estimate of the state parameter based on the CPT was plus 0.08. At plus 0.08, with the strength properties of the foundation, the whole thing fell down. Now, I think that was a limitation of FLAC, but that's what is in the ITRB report. And what we had going on is we start yielding down here, and it basically propagates upstream. It starts at the toe, and then you go over the top of the stress-strain curve. You have to dump the ability to carry stress further up, and then that fails, and the whole thing unzips. I'm going to show you a picture of that. That's the hole at the toe, and that's what it looks like. It looks bigger on the screen than reality. And that is the sort of stuff, the FRV is a couple of meters below that. Things were stepped through on the analysis, starting with 2D. And the problem with 2D, you can't put that excavation in because it was only quite localized, and then you're triggering everywhere on it. And there was also a very, as you can almost see from the way stuff flowed in, there was a strong 3D component of what was going on. So, after going along with 2D or limit equilibrium, then to 2D FLAC, you said, okay, we're going to go 3D FLAC and put all the details in. That is the failure, the extent of failure. The red line is the extent of the 3D FLAC model. The constraints, the big constraint was we had some movement markers, and we had INSAR satellite data, so we actually had a reasonable time record of movements. The plot is solid, is observed, dash is the value or the prediction from the FLAC model as the properties are adjusted. So what we're trying to do is get every one of those perfectly aligned. As you see, they're not perfectly aligned, but that was as good as was managed at the time. And that then led to this graph here, which, and it is plotted. I apologise for the lack of clarity here. This is a problem you get when you do something on an Apple and you transfer it across to an IBM PC. For some reason, despite Microsoft saying PowerPoint is PowerPoint, you actually seem to lose some resolution. Well, that is actually distance from the toe of the dam. And that was done rather than stress level, because we're then trying to communicate with the regulator and communicate with the mine owner. And we thought, well, the easiest thing to say is, let's plot the variation of strength with distance from the toe of the dam. They all could understand that. But that affects the stress level. And that is our stress and strength ratios. Blue is the peak, which is SU over sigma V naught, and black is the residual. And the solid lines is where we got to, or with the iterating with FLAC. The dashed lines are kind of a judgment looking at all the laboratory testing of what you might put forward if you were just taking the laboratory testing at face value. So the suggestion is at low stress levels, the lab tests are reasonably accurate. As you come up to higher stress levels, the strengths from the lab are overstated, and the residual was much less than predicted by the lab. Now, there's an issue of brittleness. This is a standard definition of brittleness, and I give one of the equations on the right-hand side. We basically treat brittleness as the difference between peak strength and residual strength. So a high brittleness means we're high probability of losing a lot of strength. Low brittleness is we don't get much strength loss. I now need to take you from Australia to Alberta. What you're looking at here is the Tar Island Dyke. This is in Suncor, and this is 50 years ago, a bit more than 50 years ago. And the guys then were frantically building an upstream tailings dam, which is the cross section you see down here. They had a perception that stability was controlled by the rate of rise. So they were doing a number of trials, I wouldn't call them experiments, but trials to establish safe placement procedures. As part of that, they actually had 4 failures, or 4 really quite large slumps. And bless them, they documented that in the literature. The nice thing about this is when we put an upstream raise in here, it goes in here over a period of a few months, and it's a simple dead load. Okay? Subsequent to this work in the 70s, Suncor continued to build this thing, and this dike eventually went 100 metres high. And as things went on, it became more engineered. So from about 1990 onwards, there's just a raft of CPTs and a raft of high-quality triaxial tests. But the construction procedures established in 1975 continued even to today. So, and the feedstock remained the same, and the placement of the feedstock remained the same. So we made the leap that this actually was a good case history to calibrate finite element method. So we combined observed behaviour of a slump from static loading with modern test data. This there is a sketch from Doc Hardy's notebook. He was I think a dean at the University of Alberta, and he was the original engineer of record, and that is his sketch of the largest of the slumps. And what we did, we set about analysing the slump using Plaxis, and we got some spectacular results, and there's a paper you can download and have a play with it. I don't want to go into that too much tonight because we're supposed to be talking about residual soils, but something we came up with was this. Our base case, when we took the parameters at face value and ran the simulation, we got a failure mechanism that looks like this. There's my slump, and we've got 4 metres of settlements. This is large strain Plaxis, so we get the true settlements. We've got 4.5 metres, and this is the shear strain contours. And the guys at the time said it went 200 metres upstream. That's what we computed. It's just a lovely failure mechanism that matched what they reported in 75. If I reduce G by a factor of 3, I keep the state parameter the same soil properties, the same compressibility, everything else the same loading rate, just change G, I get that mechanism. A simple, low significance rotational failure. Well, what is going on? Well, G controls two things. When you get an overload, you have to push the stresses to the adjacent soil. The propagation velocity is controlled by G. Higher G, faster it happens. G also, in most elastoplastic models, or variations of it, controls the excess pore pressure in the theory. And we've damped that down. But what it means is, if you go back to a stress strain curve, previously we were talking of brittleness was from here to here. What we found in Tar Island, that gradient seemed to be the gradient that controls. Now we discovered this 3-4 years after the Cadia. So this is not in we didn't have this in the Cadia analysis. But I think that's what was missed in Cadia. There is actually the propagation velocity is actually something we need to pay attention to. And interestingly, you've all seen Brumadinho failure where it starts over here and it just unzips. The propagation velocity in theory is approximately Vs divided by 4. Vs was measured at Brumadinho, it's about 210, maybe 215. Divide that by 4, 50 meters a second. If you go time that video and watch the propagation and you look at the distance of the dam, you get 50 meters a second. So the theory hangs together, but that means that this gradient is important. So, what started this approach to Cadia? And why was my interest tweaked in it? Well, it was started by this paper by Laurie Wesley, who wrote a paper on what should be taught or not taught in postgraduate engineering or geotechnical engineering. Laurie, if you know the new triaxial cell or the triaxial cells you use today, when they first came out they were called the Bishop Wesley cell. And Wesley is Laurie Wesley. So he was shall I say, a fairly fancy thinking PhD from Imperial College. He's actually a New Zealander. He went back to New Zealand, became part of, I think it's University of Auckland, but also had quite a consulting practice. And he spent pretty much most of his life working on residual soils. And he made the point that residual soils cover about 50% of the earth. But all our universities teach are sedimentary soils, or sedimentary ideas. And he said this really isn't good enough because sedimentary doesn't apply to residual. There's no such thing as a pre-consolidation pressure. And he said the C sub C, CS idealization doesn't work as well. And he said clays and sands are so different, there should be no common idealization between them. And then what was really worse, he said it follows from the preceding comments that critical state soil mechanics shouldn't be taught. And believe it or not, this was published by the Institution of Civil Engineers, which is almost the home of critical state soil mechanics. Now, those of you who know me will realise when I read this, the steam came out of my ears. You know, and this is just not on, because you know, if you've got something that's worked some of the time and you come up with a case where it's not working, you don't say, well, let's throw it away. You should say, what have we missed? And that would have been the correct question. So that was what was driving me. So on with Cadia, thank you, Lord, you've given me some residual soils and some decent traxel tests. That's why I got interested in doing it. And the first point, I'll quickly go through material type independence. On the right-hand side of the figure is a bunch of references and the various soil types indicated. The left are just critical state E log P stuff, and the coloured lines are the different soils. And the point I make is it doesn't matter whether you've got a sand, a silty sand, clay, sandy clay, whatever you've got. You'll get a different curve, but the same equation applies. Right? A critical state exists regardless of the particle sizes or independent of geology. And quite clearly, when we look at our tests themselves, we've got a residual critical state. You know, they plot up. As for the odometer, addressing Laurie's points on using C sub C, well, C sub C is perfectly valid up to crushing pressure. That's what the data says. Of course, you've got an OCR of 1, you've got no pre-consolidation pressure, but C sub C is fine, or some variation on it. Then you run into a regime, a constant modulus, and then you run into a collapse regime. You've got to put the 3 bits in, but don't just say, oh, it's all somehow magic, you've got to do an EP curve and work and whatever. No, there's mechanics here. We can understand what's going on. Strength is stress to latency. Again, same thing. Silt, sands, clays, whole yin-yang, the same equation in purple applies. Independent of geology. Yeah, the coefficients change. If we're in a clay, M might be like 0.9. If we're in a tailings, M's probably 1.45. But the equation doesn't. You know, Laurie's point that you can't put math to this and the math be material independent is simply wrong. State to latency, exactly the same story. Different soils, same equation applies. So, what have we done here? Well, I've taken you through a residual soil and I've applied a critical state framework to it, and I've done my best to explain how very simple ideas can be added. The ideas I've added are a crushing pressure and a degrading plastic dissipation. I have answered all of Wesley's objections and critiques. You may not realise it from me standing here and talking to you, but if you go through, I've covered all his points. Having done that, it's not good enough for me to sort of stand here and just do that. You've got to put this stuff out and say we reply. So we have put out this paper, which is now in press, in the same journal where Laurie published. I wanted to call it Critical State Residual Mechanics, but the editor just wouldn't let me have it. I thought it would be a nice play, and it's literally with residual in italics. Surely they're going to let me get away with this, but no, I got a slapping down for that. So that's where we went, and that is where we are. Questions or discussion, because some of this is new. It's not, what do you do on this? Maybe you got some ideas to tell me. Yes.
Thank you for the presentation. My question is regarding the stress strain results and end of test condition
in the written paper, we have shown photographs of every one of those triaxial tests, so you can see where the shear planes where there are. My observation is you can see it in a few of them, but a lot of them are just more like a soft plate, they're just crushed. You know, really, I think I can. I may be wrong. I believe only one shows it. 1% shows these shear. The rest are just deformed.
And for that one, did you consider the shear localization in interpretation of the results?
To be honest, when you're out to 25% strain on a traction test, it's also, what stress means. The sample's looking like this: stress in the middle end, stress on the top cap. And there's a bit of assumptions about whether we're using the barrel correction or the offset shear plane correction. I believe the offset shear plane correction is used, so we assume it's a single slip plane. Again, this is a paper. The reason why I believe, because that also came up with one review as they raised it. I was doing equations. It was doing the test data. So, yeah, or please, I believe that's it.
Thank you. I'll take it.
Come on, guys. Yes. Dan.
So when I think about shearing a structured soil and kind of destructuring it, my intuition is that Gmax should be changing. Is that correct or incorrect? What do you think about that?
I don't know if it's correct or incorrect. We didn't have vendor data on these tests. I don't know why we didn't have vendor data, in all honesty. It would have been an obvious thing to do. I don't know whether the samples, when they were so a lot of structure and they couldn't push the vendor elements into it, which could be my guess. But we were conscious that we would like vendor, but there seemed to be some reason why it couldn't be done. So my assumptions allowed them to damage their equipment by pushing vendors into what looked like rock. Because these things, when they came out, we tested them, they had like 300 kPa. You put off a penetrometer, you've got 300 kPa. They're quite rock-like and stiff. I would tend to agree with that. I think G almost certainly is bearing. Injuries are actually add that in. It would be dead easy to gain that, so that it fit the delating samples.
Might have a couple extra parameters. When does it start decaying and what rate does it decay?
Well, that's also the problem. When you do iteration, the more parameters you put in, the tougher the iteration gets, and the less you learn too. I would like to. The sad thing is, one of the reasons I was keen to come here is, as a profession, Laurie's right. We have not paid a great deal of attention to residual soils. Should any of you get to work in the tropics or somewhere where you have residual soils, if you could add something like this to the database, you'd do the profession a lot of good. You pick up all our journals. I hazard a guess that 98, not 99% of the papers are sedimentary. It's very rare to find a paper on the residual soils. Certainly nothing like we're applying these kind of things. Yeah.
Question again relating to the dead latency. Was there any bias in depth in terms of the dead latency? Was it sort of scattered evenly? You found it more often when it was a deep sample?
We didn't see anything jump out at us.
Okay.
But I've only got 7 samples, right? I think half the trouble is with these residual soils, they're quite random. And it's difficult with 7 samples, particularly where only really pulling samples from the Cadia Dam. We don't have enough distribution.
Hard to derive patterns.
Yeah. You sit here as an engineer and you can see all sorts of things. Oh, wish we could have added this and done this sort of investigation. And we could have done so much more. But review boards, you've got 6 months. You've got to get a report out, and the insurers want to know what the hell went wrong. So if we'd had an easier stratum where we could have got 50 samples, we would have been allowed to do it. This was just a toughie to find. And that's why I have sympathy for the original engineer of record. It was tough finding the stuff when you knew where to look. Ahead of time, come on. Yeah.
So Doc, yeah, you're right. I mean, when you have an accident, it's easy to see the problem, but for the engineer of record, he probably had a factor of 6
these things, we weren't allowed to talk to the engineer of record. No lawyers wouldn't answer questions, so even we provided a question to them, the lawyers would say, no, legal privilege, no answer. So we do not know what they chose or why they chose it. We discovered, for example, the very high quality piston samples in the tailings. We discovered that by accident about a document that slipped out as draft. It's really a great shame because if we could have talked to the engineer of record, we would have done both us a lot of good. We'd have perhaps learned a few things. Because I have a lot of sympathy with them. If you were to make a criticism of them, it's they pulled off the displacement monitoring. They got a little too confident that nothing was done. And that when they started putting this buttress in and markers came out and they didn't replace them. So they were blind. We weren't blind because this is an eye-opener. After the thing fell down, there was a chapman knocking on the door and said, I'm here selling satellite monitoring. And we discovered that the Airbus satellite had been monitoring the site for like 7 years. And, oh yeah. Anything you do, any job you work on, if something goes wrong, you better believe one of the satellite companies has been watching what you do, and it's on their files.
Then they can charge you.
Oh yeah, they'll charge you when you need it, but the stuff is there. And it's quite absolute eye-opening. It's like spying the sky stuff. When I first saw this, what do you mean you've been monitoring it? and then you have a company that does the processing will buy the data from, in our case they bought it from Airbus, but there are other people flying satellites, and then they process it and you get this really quite good stuff. So we saw trends that the engineer of record, if they kept the markers, should have seen, and that would then have alerted them. But the interesting thing is you were plotting up the trends, that where it turns over, when things first start going wrong, you say, oh my God, this can't be happening to me. It must be the instruments. I'll wait for the next reading to come in. The next reading comes in, you're then 2 weeks from failure. So at that point, unless you have an emergency plan ready to deploy dump trucks, there's nothing you can do. So that was certainly learning for me.
Okay.
One you out? Oh, yeah.
First of all, I'll confess I did my undergrad soil mechanics with Laurie Wesley.
Sorry, you did your undergrad?
University of Auckland. Sorry?
You.
I did my undergrad soil mechanics with Laurie Wesley.
Oh, did you?
So
Oh,
well,
right. Come up the front. Come on. No, you need to tell us more.
Well, a comment that you made early on also struck me, particularly about how this became a residual soil and the chemical weathering process. How much of the parent rock, parent vessel, was it particularly porous, and do you think that contributed to the very high void ratio in the soil, or was it purely chemically weathering?
Ian tells me, I'm blaming Ian, that it wasn't very porous at all. So all the void ratio increase was due to loss of material from chemical weathering. But you're certainly welcome to, when the paper comes out, please put in a quick written letter of discussion, because we'll then document that point, because it's not in the paper, it's a good point. Now, I have a question for you. Have I been fair to Laurie? Have I reflected his
He certainly has an interest in residual soils, and particularly from his stories like working in Indonesia and through the tropics there, especially with paving and the early flowway projects. But yeah, so I guess the thing about residual soils is
we're dealing with everything we've already complained about.
I haven't read his ICE paper, so.
Hey Mike,
Yeah.
and you guys, when you're doing the borings, you've got to the other side where things were still over there. So were you lucky to get the poor stuff there as well?
I think that's the issue. We're lucky to get any samples. Yeah, and it was particularly annoying that the health and safety was so stringent. We weren't allowed to go out and tailings to do boring. For that FRV should have gone upstream. We thought geologically there was like a channel. We should have been like, into the tailings impound. We probably would have got thick, because you remember it was sort of got thicker as you went upstream. But I think we could have got some nice borings. Literally, health and safety rules right here on the tailings bank. So it's really sad.
Were these soils CPT pushable?
Sorry?
Were these soils able to push CPT through?
We didn't attempt it. The FRV.
Yeah.
We didn't attempt it because first off above it you've got the regular basalt anyway, so you'd have to drill through that, and then I think I can't answer why we didn't. At that point, well, Ian was in charge. I think his view was it was too rock-like. He didn't think it was worth attempting. Plus, we're only trying to get this much of it. So that was that.
Well, if there's no more questions, Kenneth?
Yeah, thank you for your speech earlier, your course, and VGS would like to.
Thank you very much.
Thanks.
Thank you very much, guys. I need a beer.
Yeah.
Awesome.